session, I had introduced the concept of classification of remote sensing data. In that, two approaches, one is visual and the other digital, were introduced. In the digital image processing, the various processes involved in classifying a digital image were introduced and a brief discussion of the same was provided. Now, in this session, I am going to take one by one each of the processes as discussed earlier. The first task or process to be undertaken is the statistical evaluation of remote sensing data sets. As we know, many remote sensing data sets contain high quality and accurate data. Unfortunately, sometimes error or noise is introduced into the remote sensing data by the environment, that is atmospheric scattering, random or systematic malfunctioning of the remote sensing system, that is an uncalibrated detector creates stripping, or improper airborne or ground processing of the remote sensing data prior to actual data analysis, that is inaccurate analog to digital conversion. Therefore, the analyst should first assess its quality and its statistical characteristics. This is normally accomplished by looking at the frequency of occurrences of individual brightness values in the image displayed in a histogram, or by viewing on a computer monitor individual pixels brightness value at specific locations or within a geographic area, by computing univariate descriptive statistics to determine if there are unusual anomalies in the image data, and computing multivariate statistics to determine the amount of between band correlation, that is to identify redundancy. First of all, let us have a look at the remote sensing sampling theory. Some of the terms need to be understood before we can go in for the statistical analysis. First is population. It is an infinite or finite set of elements. An infinite population could be all possible images that might be acquired of the earth in a particular year. A sample is a subset of the elements taken from a population used to make inferences about certain characteristics of the population. If observations within certain characteristics are systematically excluded from the sample, either deliberately or inadvertently, such as selecting images obtained only in the spring of the year, it is a biased sample. Sampling error is the difference between the true value of a population characteristic and the value of that characteristic inferred from a sample. Generally, large sample drawn randomly from natural populations usually produce a symmetrical frequency distribution. Most values are clustered around some central value and the frequency of occurrence declines away from this central point. A graph of this distribution appears bell-shaped and is called a normal distribution. Many statistical tests used in the analysis of remotely sensed data assume that the brightness values recorded in a scene are normally distributed. Unfortunately, remote sensing data may not be normally distributed, and the analyst must be careful to identify such conditions. In such circumstances, non-parametric statistical theory may be preferred. Here we can see, on the basis of the information which is available, histograms can be created, and these histograms depict that around a central value, which could be the mean, median or mode, in a normal distribution case this is symmetric. However, if the mean, median or mode are different, then we may get skewed distribution. If the skewness is towards the left, then we call this as negative skewed distribution. If the skewness is towards the right, then we call this as positive distribution. Many a times there may be two peaks or two bell shaped, and this is what we call it as a multimodal distribution. When we look at the remote sensing data, it is very important to know about the data itself, and this is what we call it as metadata, that is data or information about the data. Most quality digital image processing system read, collect and store metadata about a particular image or sub-image. It is important that the image analyst have access to this metadata information. In the most fundamental instance, metadata may include the file name, the date of last modification, level of quantization, that is whether it is a 8-bit image or a 7-bit image, the number of rows and columns in the image, number of bands that the data has, univariate statistics such as the mean, maximum, mean, median, mode, standard deviation, perhaps some multivariate statistics, georeferencing performed if any, and the pixel size. Now let us look at how we go about with the assessment part. The first is viewing individual pixels. By viewing individual pixel brightness values in a remotely sensed data is one of the most useful methods of assessing the quality and the information content of the data. Virtually all digital image processing systems allow the analyst to use a mouse control cursor to identify a geographic location in the image and display its brightness value in the all data sets that are present, that is in n bands in which it has been collected. Then we can display the individual brightness values of an individual band in the form of a matrix, that is in raster form. This particular slide shows that a cursor has been placed at a particular location in the image, and corresponding to this, the next window shows that what is the location of the pixel, that is at the top where x is equal to 42, it means that this is the number of column that we are looking at, and y where the value is minus 20, it tells us that this is the number of rows, and below that the value of this particular point in terms of brightness is indicated, and the such number of points in the histogram, or that is the number of occurrences of this particular value in the whole image, is also provided. We may look at in the raster form, wherein the data would be now viewed as if it is a plethora of numbers in a gridded manner. We can also view the image in the form of 2 or 3D dimensional evaluation, wherein based on the brightness values, the elevation of the information is provided. So all those regions which are depicted in bright white would have the highest elevation in the 3-dimensional representation, whereas a dark object will be having a value of 0 and may represent a land or a surface which is at the datum level. This 2D or 3D evaluation also allows the analyst to view the image by rotating it in such a manner that the desired area can be viewed effectively. Now let us look at the various statistical tests that may be subjected to a remote sensing data set. There are two types of statistics which may be computed. First is the univariate statistics and the second is multivariate statistics. So now let us look at the various univariate statistics which are there. It could consist of computing the histogram, the cumulative histogram, finding out the minimum value, the maximum value, mean, standard deviation, skewness and kurtosis. First of all, let us look at what actually is a histogram. A histogram represents the distribution of information within a defined range. Here, for each value, the number of times that a value occurs or existed is counted. This number of occurrence is known as frequency. When these frequencies are plotted with the values on the x-axis and is associated frequency on the y-axis, then the resulting plot is known as a histogram. If each frequency is represented by a dot, its resultant appearance is in the form of a curve. If the frequency is represented by a line, then the resultant appearance is in the form of a series of skyscrapers. In image processing, histogram is useful information and is used at various steps of image processing. Since the image data is an independent distributed set of samples from a random process, it is often convenient mathematically to assume that the histogram is Gaussian in nature. Here the distribution is centered about the mean value and its width is proportional to its standard deviation. This distribution can be expressed by this relationship, that is fx, that is the frequency of a particular value x, can be expressed as 1 divided by sigma multiplied by under root 2 pi exponential raised to the power minus x minus mu whole square divided by 2 sigma, where sigma is the standard deviation and mu is the mean value. These parameters will be discussed later. One thing which can be seen regarding the histogram is that it is symmetrical about its central axis and that it has a direct correlation to the standard deviation. The shape of the histogram provides information regarding the number of features within an image. Generally, histogram of an image is typically unimodal in nature, that is, it has a single peak with extended tails at the both ends. However, in the presence of multiple features in an image, the histogram may be multimodal, that is, there are many peaks where each peak represents a feature. However, it may not be possible to clearly identify or pinpoint which peak represents a particular feature. Further, it may be noted that an image histogram only provides the frequency at each level, but not the spatial correlation. Image histogram is a very useful geographical representation of the image information content. Based on this information, the contrast of an image can be improved. That is, the appearance on a display device can be improved by having the input information regarding the distribution of information represented by a histogram. The next parameter is cumulative histogram. Some of the contrast enhancement techniques such as histogram matching or histogram equalization require cumulative histogram. It is the sum total of all the frequencies up to that value and generally expressed as a fraction or as a percentage of all the frequencies in that particular image. Next is determination of the minimum and maximum value. The minimum and maximum value are an indirect indicator of the quality of the image. The minimum value indicates whether the image is affected by atmospheric effects. For an 8-bit image having 256 levels of information, the minimum value is 0 and the maximum value is 256. If the minimum value is equal to 0, then the image is not affected by atmospheric effects, whereas if the minimum value is more than 0, the quality of the image may be affected and the quality of the image may not be good, and it is affected by atmospheric effects. The next statistical parameter to be determined are the mean and the standard deviation. The mean of a statistical distribution with a discrete random variable is the mathematical average of all the terms or values in an image. To calculate the mean, all the terms are added up and then divided by the number of terms in the distribution. This type of mean is also called the arithmetic mean, or more commonly known as average. The mean of a statistical distributor with continuous random variable is the value of that random variable denoted by the lower Greek letter mu. So, mean can be expressed as 1 divided by n summation of all the points within the given data set. Next is standard deviation. Standard deviation is the root mean square deviation of the values from their arithmetic mean. Standard deviation is the most common measure of statistical dispersion, measuring how the values in a data set is distributed. If the data set points are all close to the mean, then the standard deviation is close to 0. If many data points are far from the mean, then the standard deviation is far from 0. If all the data values are equal, then also the standard deviation is equal to 0. A large standard deviation indicates that the data points are far from the mean, and a small standard deviation indicates that they are clustered closely around the mean. Well, standard deviation can be expressed by the following relationship, that is, by taking the square root of 1 by n minus 1 and taking the summation of the difference between the input value minus the mean and taking the square of this particular difference. The mean and variance are sufficient to specify a normal or Gaussian distribution, and the area under the probability distribution function curve is symmetrical about its mean, that is mu. If the histogram is unimodal and symmetrical, a Gaussian distribution may be an appropriate model for representing the actual data. However, histograms of an image tend to be asymmetric and also multimodal in nature, and hence information about mean and the standard deviation is useful to the analyst. Further, standard deviation can be used as a measure of image contrast, since it is a measure of the histogram width, that is, the spread in the brightness values. This particular slide shows the area under the normal curves for various standard deviations from the mean. The first graph shows the area under the normal distribution curve with the range of 1 plus minus 1 sigma. It is observed that in a normal distributed data set, this would be 34% about the mean on both the sides, that is, the total area coverage under 1 sigma with respect to mu is 68%. When this is increased to 2 sigma, the area under the curve increases to 95.4%, and if the 3 sigma condition is taken, then we find that the area under the normal distribution curve is 99.73%. Basically, one has to understand what does this represent. It just tells us the compactness with which we would like to adhere to our data set, and also it gives an idea as to the rejection criteria. For a 1 sigma spread about the mean, about 32% of the data is considered to be a part of the error system. However, when it is increased to 2 sigma, then this is only 44.3%, and for 3 sigma this is very much less, of the order of about 0.27%. That means only nearly 0.3% of the data is to be considered as outlier, or what we can call it as noise in the data. The next parameter to be examined is the skewness. It is a measure of the asymmetry of the probability distribution of a real valued random variable. A distribution has positive skew or right skewed and negative skew or left skew if the left tail is longer. The skewness can be calculated using the following formula, that is 1 divided by n, taking the summation of all the points in the data set of the difference between the input value minus its mu divided by sigma and taking the cube of the same. Skewness is 0 for any symmetric histogram. A histogram with a long tail towards larger brightness values has a positive skewness, as shown in the graph below, and this is very typical of the remote sensing data sets. Next is kurtosis. A histogram may be symmetric, but it may have a peak that is very sharp, or that is, it is subdued when compared with a perfectly normal distribution. A perfectly normal distribution histogram has 0 kurtosis. The greater the positive kurtosis value, the sharper the peak in the distribution when compared to a normal histogram. Conversely, a negative kurtosis value suggests that the peak in the histogram is less sharp than that of a normal distribution. So, it can be said that it is a measure of the peakness of the probability distribution of a real valued random variable. Higher kurtosis means more of the variance is due to infrequent extreme deviations as opposed to moderately sized deviations. Kurtosis can be expressed by the following relationship, that is 1 divided by n, taking the summation of all the n points in the data set of the difference between the input value minus the mu divided by sigma raised to the power 4, and this expression is subtracted by a value of 3. The higher kurtosis distribution has a sharper peak and the fatter tails, while a low kurtosis distribution has a more round peak with wider shoulders. The same has been shown in the 2 graphs depicted below. A higher kurtosis has a higher peak along the central value, whereas lower kurtosis is more bell shaped and the shoulders are much more rounded. Having had a look at the univariate statistics, now let us look at the multivariate statistics which are there. Here we are now going to take, instead of one data set, we are going to compare it with another data set. This examination can be performed by plotting scatter plots or by computing covariance or correlation. First of all, let us look at what is a scatter plot. A scatter plot is a useful summary of a set of bivariate data usually drawn before working out the linear correlation or fitting a regression line. It gives a good visual picture of the relationship between the two variables and aids the interpretation of the correlation coefficient or the regression model. Each unit contributes 1 point to the scatter plot on which the points are plotted but not joined. The resulting pattern indicates the type and the strength of the relationship between the two variables. The scatter plot, based on its trend, can be categorized as positive association between two variables, wherein we would find a upward trend, that is a positive slope, where small values of one variable is related to the small value of the other variable. A negative association would be indicated by the opposite effect, that is a negative slope, where most high values of one variable is related to the lower value of the other variable. Non-association is where the values of one variable exhibit no trend with the other variable. The next multivariate statistic parameter to be estimated is the covariance, and this is in the form of a matrix in case where we have n number of data sets contained within a particular image. In remote sensing, we normally have more than one band of information. So, a covariance matrix is a matrix which provides us a detailed form of the error estimate of the data and is also known as the variance covariance matrix. A complete covariance matrix is symmetrical about the diagonal elements, that is, same values appear on both sides of the diagonal elements. Covariance matrices contain information about the absolute and or relative accuracy of the data elements, that is coordinates. The absolute accuracy information is contained in the diagonal matrix elements. The relative accuracy is a function of the multiple diagonal and the off diagonal terms. A complete covariance matrix of n specific points in 3D space would contain n number of rows, 3n rows by 3n columns. For example, for a 3 coordinate, a covariance matrix is a 3 by 3 matrix with the matrix rows and the columns each corresponding to the 3 coordinates. For just 2 horizontal coordinates, a covariance matrix is 2 by 2 matrix with the matrix rows and the columns each corresponding to the 2 horizontal coordinates. Similarly, for 2 image coordinates, a covariance matrix is a 2 by 2 matrix with the matrix rows and columns each corresponding to the image coordinates. Here we see a typical representation of a covariance matrix for a 4 band remote sensing data sets consisting of band 1, 2 and 3. The diagonal elements are represented by the square of the standard deviation, which is also known as the variance, whereas the off diagonal terms are represented as the interrelationship between variable 1 and 2 or between 1 and 3 or 1 and 4, and similarly we find that the variation for the second band with respect to the other can be represented as covariance 2-1 or 2-3 or 2-4. So, what does this covariance 2-1 actually means? This can be represented in the general form, that is, between two variables I and j, the covariance between them can be expressed as the sum of the products between the two variables I and j divided by n minus 1, which can be further expanded and simplified as n summation of the cross products of a single value in both the variables I and j minus the sum of the variables in variable 1 and the summation of variable 2 whole divided by n minus 1, where n is the total number of pixels in the image and ki is nothing but the brightness value of the kth pixel in band I, and kj is the brightness value of the kth pixel in band j. Having computed the covariance matrix, we then compute the correlation matrix. Correlation matrix is also known as the correlation coefficient, and it indicates the strength and direction of a linear relationship between two random variables. In statistics, correlation refers to the departure of two variables from independence. There are several coefficients measuring the degree of correlation adapted to the nature of data. The best known is the Pearson product moment correlation coefficient, which is obtained by dividing the covariance of the two variables by the product of their standard deviation. So, for two variables I and j, the correlation coefficient can be expressed as Rij is equal to covariance Ij divided by the standard deviation of variable I and standard deviation of variable j. The correlation coefficient is a ratio, and hence it is a dimensional parameter, and it ranges between -1 to +1. The correlation is defined only if two variables have a definite standard deviation and both of them are non-zero. It is a corollary of the Cauchy-Charvag inequality that the correlation cannot exceed more than 1 in absolute value. The correlation is 1 in the case of a increasing linear relationship, while it is -1 in case of a decreasing linear relationship, and some value in between in all other cases, indicating the degree of linear dependence between the two variables. Closer the coefficient is to either -1 or +1, stronger is the correlation between the variables. If the variables are independent, then the correlation is 0. But the converse is not true, because the correlation coefficient detects only linear dependencies between two variables. In image processing, variance covariance and correlation matrices provide an insight to data redundancy and are used in principal component analysis, feature selection and classification. Having had a theoretical description of the various parameters which help us in identifying what is the characteristic of an image in terms of its statistical nature, now let us understand all this by undertaking a small illustrative example. Here a TM data set for a particular area has been taken, and the sixth band, which is the thermal data, has not been taken into consideration. The rest other, that is TM band 1, 2, 3, 4, 5 and 7 have been taken for analysis. The seventh image which we see in the color is the false color composite, wherein 3 bands have been taken where the brightness values of each of the bands have been projected in a particular color to create a color image. We call this false color because it is not the absolute measure of the information, but it is the reflected energy of the information that we have. So, we will be now undertaking the analysis of the 6 bands of the TM data set. In order to do this, IDAS Imagine software has been used to compute the various variables. This particular table shows the various statistical parameters which have been discussed earlier. These are the univariate statistics for all these 6 bands 1, 2, 3, 4, 5 and 7, and we find that the minimum value in band 1 is 44, in band 2 it is 25, band 3 it is 13, 6 in band 4, 1 each in band 5 and 7. Similarly, the maximum values are 147, 139, 183, 164, 227 and 255 respectively. The mean has been computed for each of these bands and it is 66.1, 51.84, 49.73, 70.78, 65.08, 44.53 respectively for the 6 bands, with a standard deviation of 10.01, 12.01, 18.13, 12.93, 21.56 and 22.51 respectively for the 6 bands. The median is 65, 50, 45, 71, 62, 38, while mode is 67, 53, 36, 72, 59, 29 respectively. Having obtained these values through the software, now we have to interpret what actually these values provide us in terms of a qualitative measure of the quality of the data. We observe that TM bands 1, 2 and 3 have high minimum value, an indication of atmospheric scattering resulting in an offset to the brightness values to the darkest object in the image. This is not evident in TM band 4, 5 and 7 because atmospheric scattering is negligible in infrared bands. Hence, removal of atmospheric effects has to be undertaken for TM band 1, 2 and 3. Well, this is a very conclusive decision or information that one has now derived. The maximum value of TM band 1, 2, 3, 4 and 5 reveals that the full brightness scale is not being utilized and hence the image may have a poor background and may require contrast enhancement. Now we look at the histogram of all the 6 bands that we have. The mean values of all the bands are skewed from the central value of the brightness scale. A critical examination of the histogram shows that especially in TM band 1, 2 and 3, the information is concentrated within a small range of the brightness value and has multimodal distribution. For TM band 4, 5 and 7, the histogram has a wider base and unimodal in nature. This implies that in case of band 1, 2 and 3, a contrast enhancement, if undertaken, will enhance the features on the brighter side of the scale, since the maximum values are closer to the central value of the histogram. In case of the other bands, little or no improvement in the image quality may be there if contrast enhancement is undertaken. So, another process in image processing has now been understood by examining the initial statistics of the data set. Now we examine the covariance matrix. Here we find that the diagonal terms are nothing but the square of the standard deviation or what we call it as variance. Variance is nothing but it is like entropy as in thermodynamics, which tells us the amount of heat energy. Similarly, in remote sensing, this tells us the amount of information content available in each of the data sets. So, if we really look at these diagonal terms, band 1 probably has the lowest value, that means it has the lowest information content in comparison to band 5 and 7, where the values are very high. The off diagonal terms, which indicate the deviation from the central value, and they represent a form of interdependency or independence from each variable. However, the analyst may not be able to derive any plausible information by only examining the covariance matrix, because this is an unscaled information. In order to have a scaled information, this covariance matrix is subsequently converted into a correlation matrix. When we look at the correlation matrix, probably all the information has now been scaled between the range of -1 to +1, as already indicated earlier. And what we find that all the diagonal terms are having a value of 1, because we are comparing the same variable to itself. However, when we look at the comparison between or the correlation between band 1 and band 2, or between band 1 and band 3, what we find is that the value is close to 1. In case of band 1 and 2, the correlation is of the order of 0.97, or in case of band 1 and 3, it is of the order of 0.94. Similarly, between band 2 and 3, we find it to be of the order of 0.97. Well, what does this mean? Well, it is a clear indication that the information contained between these variables, that is the TM band 1, 2 and 3, are similar, more or less similar, and thus there is no additional or extra information which is present in these data sets, which gives the analyst another indication that out of these 3 data sets, any one of them can be used subsequently for classification of the image. A very unique trend may be observed with TM band 4, and it reveals that the correlation amongst the other 5 data sets which is there is probably of the lowest order, of the order of 0.25 and so on, which means that band 4, when it is compared to all other bands, it contains altogether a very different information. And this is a very positive conclusion which can be drawn, and that is that when we are proceeding for classification of the image, wherein we will be using a multispectral data sets, that is large number of data sets would be taken, a minimum of 3 is required. So, it means band 4 is a strong candidate in the whole analysis procedure. However, when we look at the correlation between band 5 and 7, what we find, it is of the order of 0.94. That means these 2 data are strongly correlated and hence are redundant. And thus, now what we can understand is that out of band 1, 2 and 3, either one of them can be selected. Amongst 5 and 7, one of them can be selected, and band 4 being one which is totally distinct in nature. Now, we look at the scatter plots. Here, the scatter plots between all the data sets have now been plotted. One can see In some of the cases, the spread of the information is like a very fine line, and in some cases it spreads out into a triangular shape. Since we have already derived one information, that is the correlation between band 1 and 2 or band 1 and 3 or between 2 and 3 is very high, the same trend is also depicted in the scatter plots. So, if we look at the scatter plots between TM1 and 2 or 1 and 3 or between 2 and 3, we find the spread is along a line, along a elongated line, but at an inclination from both the axes. This is primarily because of the offsets that may have been produced by the atmospheric effects, which has been reflected in the terms of minimum value. However, if we look at the scatter plot between TM band 4 and the other TM bands 1, 2, 3, 5 and 7, we find that the spread of the information is in a triangular shape. That means there is a very plausible information which is available, and the spread of the information is very well distinct and can be utilized subsequently by the analyst to identify the plausible information classes which are present there. So, based on the observations that we have had up till now in this particular example, we can make some concluding remarks. That is, on the basis of univariate statistics, it can be stated as follows. TM band 1, 2 and 3 are affected by atmospheric scattering. The contrast enhancement will improve the image quality of TM band 1, 2, 3 and 4. The mean value indicates that the brightness of the image will increase in all the bands. The multivariate statistic shows that TM band 4, 5 and 7 have more information content compared to TM band 1, 2 and 3. TM band 4 has low correlation with all bands, while TM band 1, 2 and 3 are highly correlated to each other, and thus either of them can be used. Scatter plots show that TM band 4 with all other bands has a good spread of information. With this, we have now made a assessment of the quality of the data. In my next session, I would be looking at some of the pre-processing which are required in order to provide a strong spatial correlation of the data set to the actual Earth of which the image has been taken. Thank you.